So welcome again to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but we also see and appreciate the beauty in the simpler problems. So today, we are continuing on this new topic of exponents slash logarithms. And we're still on the MIT 2022 Integration B regular season. The problem that was fascinating to us today was problem number 13 from the 2022 Integration B regular season set of questions. And it's a very interesting problem. So it's the integration from x equals to 0 to x equals to 1 of the square root of 1 over x times the natural logarithm of 1 over x. So thank you for joining us today. Before I jump into trying to come up with a solution, I would like to thank our subscribers. Thank you so much for the continued support. We are growing, as I always say, and we do appreciate your support. We don't take your support for granted. And that's why we come here at least every day or every other day to try and bring these solutions to you. For our first-time visitors, we do encourage you to subscribe. We do really would appreciate your support. That would go a long way in giving us the extra visibility that we need. If you're here for the second, third, or fourth time and haven't gotten that extra confidence to subscribe to our channel, we are going to be here. So we encourage you to subscribe. We'll need your support. The support will go a long way in giving us that extra motivation to always come back here. So I'm jumping into the solution for this problem. As you can see, it looks intricate. The first thing, as I always say, at least for me, is when I see things that look similar, I would like to substitute them to, a variable that is simpler. So what I would do is I'll say let u be equal to 1 over x, and that means that du dx is negative 1 over x squared, meaning that now du dx is equals to negative u squared. And so we can divide both sides by negative u squared and also multiply across by dx. And so that negative du over u squared is equals to dx. So what this means is that in this original integral here, we could substitute for dx with du over u squared negative. Now there's a slight representational issue here. This dx has to be out of the square root sign. So if you're OCD and your nerves are shouting, just imagine that this dx is out of the square root sign. So with this substitution, what happens is when x tends to 0 at this lower limit, then u tends to infinity. That is obvious. And then as x tends to 1, 1 over 1, so u tends to 1, okay? So therefore, our integral, again, this dx is out of the square root sign, is going to be now, in the lower limit, we say it was infinity, and then the upper limit is 1. Square root of 1 over x is u, natural logarithm of 1 over x is another u. So, and then dx is substituted with a negative du over u squared. So next thing is this u and this u squared and this square root of u can interact in such a way that we now have the integration from, again, looking at this negative here means that we can flip the limits. So it's now the integration from 1 to infinity of u to the power negative 3 over 2 times the square root of natural logarithm of u. So that is where we are. The next thing that I am inclined to do is I would like to pull this logarithm sign out of the square root sign. And what I would do is say let another variable t squared be equal to log u, such that when I insert t squared in here, we have just a t. So square root signs to me sometimes tend to be painful, so I like to get rid of them whenever I could. Such that now if t squared is equals to log u, then e to the power t squared is equals to u. And so 2t e to the power t squared dt du is equals to 1. And so that means that when you multiply across by du, then we have 2t e to the power t squared dt being equal to du. So we can substitute for du with 2t e to the power t squared dt. Now with this transformation, now we can say when u tends to 1, the lower limit here, then t is 1, and then t is equals to, t squared is equals to log of 1, so therefore t tends to 0, since logarithm of 1 is 0. And then as u tends to infinity, t also will tend to infinity. Therefore, this integral now becomes the integration from t equals to 0 to t equals to infinity. In place of u here, we have e to the power t squared. Now we have the power negative 3 over 2 there, so we keep that there. And then the square root of log u now is square root of t squared, which becomes t. And then in place of du, we have 2t t e to the power t squared dt. And that's what we've done. And so now consolidating the t's and consolidating the e to the power t squared is what we're going to try and focus on. When you multiply this exponent negative 3 over 2 times t squared, we have negative 3 over 2 t squared, and then we have another t squared here. So eventually we're going to be left with a negative a half. So you see here we're adding these exponents, and then the t's here have been consolidated, and then the constant has been pulled out, shown here. Okay, so we have 2 times the integration of t from t equals to 0 to infinity of t squared times e to the power negative t squared over 2. Now we're going to use the Gaussian integral, and the Gaussian integral, one-sided Gaussian integral, is what we'll focus on. But before that, I'd like to show a few things. In order to eliminate this t squared, we're going to try and use integration by parts. And by doing that, I just have conveniently separated 1t here into bracket with this t to the power, e to the power, negative t squared over 2, and then we've kept 1t out. Now, since we have a negative here, I have introduced another negative here artificially. So what we'll do now would say let u be equal to this t, and let, so that du is equals to 1, and then let dv be equal to this negative t times e to the power negative t squared over 2, such that our v is just e to the power negative t squared over 2. And when you differentiate this, you get back here. So using this popular formula of integration by parts, where if you're integrating a product of u and dv, then the integration is uv minus the integration of v du. Since we have all our u and v and dv and du, so we considered u to be t and dv to be negative t times e to the power negative t squared over 2. Therefore, we're keeping this constant negative 2 out, and then we have these curly brackets, and then this initial uv is obviously ut, and then v being equal to e to the power negative t squared over 2. And then we have these limits in place. And as we can see, when t tends to 0, this entire thing goes to 0. When t tends to infinity, because e to the power negative t squared over 2 tends to 0, so the entire thing goes to 0. So this entire initial component just collapses to 0, and therefore we have negative 2 here times negative the integral of e to the power negative t squared over 2. So our integral now just reduces to twice the integral from t equals to 0 to t equals to infinity of e to the power negative t squared over 2. Now, this is where now we're going to employ the Gaussian integral, the half of the Gaussian integral, where if you have the integral from x equals to 0 to infinity of e to the power constant a into bracket x plus b squared dx, then that is half of the square root of pi over a. Now, here, when you look at this here, our a is half, our b is 0, and so our answer is going to be keeping this constant here twice, and then keeping this half here, half times the square root of pi over a. Our a is half, so over half. And so this 2 and this half cancel, so we're left with 1. And then since we have a half in our denominator, this 2 goes up. And so our answer becomes the square root of 2 pi. And that is the answer for the seemingly benign problem, but quite intricate. Thank you so much for those of you who are with us and followed us all the way up to this point. Thank you. And for those of you who have not subscribed yet, we encourage you to subscribe. It's been an absolute pleasure hanging out with you, solving this problem. Until next time, adios.